Hello everyone, this is Anushka and my roll number is 205015 and my topic for today is group theory. Before starting with the main topic that is group, let us understand what algebraic structure is. So it is defined as a non-empty set G equipped with one or more binary operation. Now suppose star is a binary operation on G, then G star is an algebraic structure. For example, consider the set of natural numbers n under the operation addition, then n plus is an algebraic structure. Similarly, we have other examples as well. Now consider this example r plus star. This is an algebraic structure which is equipped with two operations, that is addition and multiplication. Now let us understand what binary operation is. So for this we consider a set G and an operation star, and for this operation star to be a binary operation it must satisfy the following condition. So for this we consider any two element from G, suppose A and B, and if we operate it as A star B and whatever we get belongs to G, then star is said to be a binary operation on G. Or in other words, we can say that G is closed for the operation star, then star is a binary operation on G. Next topic is semigroup. An algebraic structure G star is called a semigroup if the binary operation star is associative in G, that is, if bracket A star B bracket close star C is equal to A star bracket B star C for every A comma B comma C belonging to G. It means that if associativity property holds as well as closure property holds, then it is said to be a semigroup. For example, consider the set of natural numbers under the operation addition, and we know that addition is an associative operation. So the set n plus will be a semigroup. Similarly, we have other examples as well. N star, I plus, R plus, these all are examples of semigroup. Next topic is group. So first its definition. Let G be a non-empty set equipped with a binary operation denoted by star. That is, A star B represents the element of G obtained by applying the said binary operation between the elements A and B of G taken in that order. Then this algebraic structure G star is a group if the binary operation satisfies the following postulates. First one is closure property, which means A star B belongs to G for every A comma B belonging to G. Second one is associativity, that is bracket A star B bracket close star C is equal to A star bracket B star C for every A comma B comma C belonging to G. Third one is existence of identity. There exists an element E belonging to G such that EA is equal to A is equal to AE for every A belonging to G. The element E is called the identity. Fourth one is existence of inverse. Each element of G possesses inverse. In other words, A belongs to G. This implies there exists an element B which belongs to G such that BA is equal to E is equal to AB. The element B is then called the inverse of A, and we write B is equal to A inverse. Thus, A inverse is an element of G such that A inverse A is equal to E is equal to A inverse. Now, if all these four postulates is satisfied, then the given algebraic structure will be a group. In continuation to it, we have abelian group or commutative group. This is defined as a group G is said to be abelian or commutative if, in addition to the above four postulate, the following postulate is also satisfied, which is commutativity. That is, if AB is equal to BA for every A, B belonging to G. This means that if this condition is satisfied, then the group will be known as abelian group or commutative group. Now the next topic is finite and infinite groups. Definition: if in a group G, the underlying set G consists of a finite number of distinct elements, then the group is called a finite group, otherwise an infinite group. The number of elements in a finite group is called the order of the group. An infinite group is said to be of infinite order. We denote the order of a group G by the symbol O in bracket G. It should be noted that the smallest group for a given composition is the set E, consisting of the identity element E alone. Now the next topic is some general properties of groups. Suppose the group consists of a non-empty set G equipped with a binary operation denoted multiplicatively, then we have some following properties or theorems. First one is uniqueness of identity. The identity element in a group is unique, which means that there is only one identity element in a group. Second one is uniqueness of inverse. The inverse of each element of a group is unique, which means that one element cannot have two inverses. Now here is a note: the identity element is its own inverse, since we know that EE is equal to E, therefore E inverse is equal to E. Theorem 3. If the inverse of A is A inverse, then inverse of A inverse is A. That is, A inverse inverse is equal to A. Now fourth theorem is reversal rule, which states AB inverse is equal to B inverse A inverse for every A, B belonging to G. That is, the inverse of the product of two elements of a group is the product of the inverses taken in the reverse order. Theorem 5. Cancellation law hold good in a group. If A, B, C are any elements of G, then AB is equal to AC. Then by left cancellation law, A will be cancelled and B is equal to C. And if BA is equal to CA, then by right cancellation law, A will get cancelled and we will get B is equal to C. Theorem 6. If A, B are any two elements of the group, then the equation AX is equal to B and YA is equal to B will have unique solutions in G. Theorem 7. The left identity is also the right identity. That is, if E is the left identity, then also AE is equal to A for every A belonging to G, which means E is also the right identity. Theorem 8. The left inverse of an element is also its right inverse. If A inverse is the left inverse of A, then also A inverse is equal to E, which means A inverse is also the right inverse of A. Now here is an example. In this we have to show that the four fourth roots of unity, which are 1, minus 1, I and minus I, form a group with respect to multiplication. So first we write G is equal to 1 minus 1 I minus I. Now we make up a composition table for this, in which we write these elements in first in horizontal rows and then in vertical columns and then solve it. Like 1 into 1 will be 1, 1 into minus 1 is minus 1, 1 into I is I, 1 into minus I is minus I. And similarly, we do it for all of it. Now, then we check all the four postulates to see if it is satisfied. First one is closure property. Now we can see that all the elements which are here belongs to this set G. That means there are no foreign elements present in this set. So we can say that G is closed with respect to multiplication. Therefore, multiplication is a binary operation on G. Next one is associativity. The elements of G are all complex numbers and the multiplication of complex number is associative, so associativity also holds here. Third one is existence of identity. Now we can see that 1 is the identity element here because if we multiply anything with 1, we get the same element itself. So 1 is the identity element. Now existence of inverse. So we see that inverse of 1 will be 1 because inverse of identity element is is the element itself. Now next one is minus 1. So inverse of minus 1 will be minus 1 since minus 1 into minus 1 is equal to identity element which is 1. Third one is inverse of I. It will be minus I since minus I into minus I is equal to identity element 1. Now for inverse of minus I we have I, that is minus I into I is equal to 1, which is the identity element. So we see that inverse of all the elements exist in this table. So we can say that the group G, we can say that G is a group with respect to multiplication. Now we can also see that commutative property holds here since we know that multiplication of complex number is commutative. Or we can also check it as first we take the principal diagonal this and then we compare the elements present on this side. 1 minus 1 I and minus I as minus 1 I and minus I, minus I as minus I and 1 as 1. So we can say that commutative property holds here. So the group G is also an abelian group with respect to multiplication. Here it is written the same, that is existence of identity and existence of inverse. So G is a group and also G is an abelian group of order 4 since there are 4 elements present in the group. And this was the end of my presentation. And thank you so much.